All right, welcome. So today we're looking at an activity that is very similar to what we did in our previous lesson. Only this time, instead of looking at angles of polygons, we are looking at areas of polygons. And so today we're specifically looking at areas of regular polygons, which means that all of the sides and angles will be congruent. We're going to try to develop some sort of method or formula that'll work for a regular polygon regardless of how many sides it has. So for today's demonstration, we've got 4 figures to look at. Let's assume that each polygon has a side length of 4 units. And basically, I just picked that number out of a hat just to give us something to work with. What we're going to do is use the known formula for finding the area of a triangle, which we know is 1/2 base times height. So let's start things off with a triangle. It's regular, so that means it's equilateral. And we know all the sides are 4. We know that the base and height are always going to be perpendicular. And we know that any side can technically be used as the base. So if we're looking at this picture, we know that the base is 4, but we're missing the height. So if we choose a side to be the base and we draw a little altitude, we know that we are going to need to find that length in order to get the area of the triangle. So besides just having the area formula for the triangle, the other thing that we're going to need is trigonometry. Sine, cosine, and tangent. I know this figure is equilateral because I said it was earlier. The prompt gave us that these are all regular polygons. And from our previous lesson, we know that we can find the angles of any regular polygon. So what I'm going to do is go ahead and mark that there's 60 degrees at each of these corners. And if I notice, what I've done is created a little right triangle with a 60-degree angle at the bottom corner. And I've sort of split that base in half. So let's say that since the total was 4, the little green line has a length of 2 units. So at this point, I can solve this using special right triangles. But for the sake of consistency and something that's going to work every time, I want to use trigonometry instead. So I'm looking for the height. I know the height of the triangle is opposite the 60 degrees. So if I look at what I know, I should be able to say that the tangent of 60 degrees is equal to the opposite leg, which is my missing height, over the adjacent leg, which is 2. And from what we did before, we know we can use cross multiplication to find the value of h. We always need to make sure that since we're dealing with degrees, our calculator is set to degree mode. And if I do that, I should get h is about 3.5. And I'm doing decimals because while certain angles will give us nice clean values, most of them will not. So let's go ahead and just round things to the nearest tenth for our final answers. So our area, therefore, 1/2 of 4 times the height, which we got was 3.5. So when I do this on my calculator, I'm going to, instead of typing 3.5, I'm going to use the entire decimal by copying and pasting it down. That way my rounding doesn't actually affect anything until the very end. So the area would be about 7 units squared. All right, so let's do that for this guy right here. Continue forward, looking at the quadrilateral. So once again, we're going to assume that there are 4 units on each side. And what I want to do is split this guy into triangles. Now I could go all the way across the center, but for the sake of consistency, I want to draw this out and show you guys how to do it if we draw all of the figures from the center itself. So let's focus on one triangle at a time. Let's say I can get this right here. I know that's 4 units long. That can be my base, but I need a height. I know that the central angle is 90 degrees here. And I know this because if I was to trace from one point and go all the way around, it would make a full circle. Full circles are 360 degrees. 360 split into 4 equal angles is 90 degrees. Thus, that's my central angle. Thinking about what we did in the previous example, if we focus on one triangle at a time, it splits the base in half, but it also splits this central angle in half, right? Because that 90 degrees went from this to this. So inside the little green triangle, there's only really 45 degrees. And this brings us back to where we just were, right? So we can say that the tangent of 45 degrees is equal to the opposite leg, which if you look at the position now is a 2, which puts the height at the adjacent leg, and we're just going to cross multiply. So the height is going to be 2 divided by tangent 45. So if I type that in my calculator, I get that h equals 2. Again, we could have used special triangles to do this, but we want a method that's going to work all the time, not just some of the time. So h is 2. So the area of the one triangle is half of the base, which is 4, times the height, which is 2. So we got a total of 4 units squared. But that is only for one of those 4 triangles. So to get the total for the whole figure, I'm just going to take that number and multiply it by 4 because there's 4 triangles in the figure. So 4 times 4, and that gives me 16 square units. Alright, so let's do the Pentagon, and then hopefully we'll start to see what the pattern is. So we want to do the same thing. We need to go split it into triangles. Our triangle needs a base and a height. So again, the base is 4. Here's our height. So if I want to get those central angles, again, I'm going to take 360 degrees, this time divide it by 5. Gives me 72 degrees. So that means each of these guys is 72 degrees. Which means that my little green triangle only has 36 degrees. So if I want the area of one triangle, first I need to find the height. So tangent 36 equals the opposite leg, which is 2. This guy. Over the adjacent leg, which is the height. And there we go. So if I take 2 divided by 1036. I get about 2.8. So the area of one triangle will be 1/2 of the base times the height. But if I want the whole figure, I got to count all the triangles, right? So there are 5 triangles. So I multiply all that together, and I get that the total area is 27.5 units squared. Okay, so let's try to generate a formula. So the first thing we want to realize is that we have a special term for the distance from the center of a polygon to its base. And that term is the apothem. So when we adapt our formula, what we're going to do is use an A instead of an H. But if we look at the method that we used, we took the area of the triangle, which is 1/2 of the triangle's base times its height, and then we multiplied by the number of triangles. Fair enough. Said a second ago that the distance from the center of the polygon to its base is called an apothem. So what I'm going to do is change the H to an A. So we have the base of the figure times the apothem times the number of triangles. And if we notice how the number of sides and the number of triangles to the figure compare, looks like it's always going to be the same. Right? So if we draw our lines from the center of the polygon, the total number of triangles will always equal the number of sides. Also, the base of the triangle is equal to one of its sides in length. So if I think about it, if I take all of the sides of the triangle, of the polygon, multiply it by the number of sides, that's just going to give me the total length of all of the sides going around the polygon, which we can shorten to the perimeter. So the shortcut, the formula that always works for any regular polygon, is the area is equal to 1/2 of the apothem times the perimeter. That's all we have for today. See you guys next time.